Hi, I'm Mrs. Hickman, and today we're going to be talking about continuity. So let's first do an example that I already traced out for us. So we're going to do the limit as x approaches 2 of f of x is going to equal negative 1. Okay, so if we draw a graph up here, I have 2, and then I have negative 1. So something around here is going to hit. But watch over here because I also have a defined point at f2. So f of 2 equals 2. And I have some limit that exists right here, and that's going to have to be a whole, but that just means something from the left and something to the right is going to meet here. Then we're going to have the limit as x approaches 4 on the right-hand side is going to positive or negative infinity. So there's 4, so to the right it's going to negative infinity. And on the left it's going to positive infinity. The limit as x approaches positive infinity, or the right-hand side of the graph, is pointing upward. So I'm just going to point that in that direction. The limit as x approaches negative infinity of f of x equals 2. So this is saying the left-hand side of the graph is going to be approaching 2. So since I'm going to be down here, I'm probably going to be drawing something from here to there. So there's 2. Yeah. So there we go, and then we go something like that. Okay, so that's one example of how you could graph that graph. Here's a bigger one down here if you would like to see. Okay, so let's go to continuity at a point. So a continuous function is any function y equals f of x whose graph can be sketched in one continuous motion without lifting a pencil. Okay, a continuity are all points at which a function is continuous. So if we're looking at this graph right here, we're saying that it is continuous from 1 to around 1, and then it goes 1 to around 2, 2 to 4. Okay, another way you could say this is f is continuous at every point in its domain 0 to 4 except at 1 and 2. Alright, continuous points, so you're going to want to check the endpoint and the interior point limit. So you're going to see if there are going to be defined points and if the limit exists. So of course the limit exists from here, and it also exists over here. Okay, so let's look at our discontinuous points. Let's see if there is a limit at x equals 1. So the limit on the left-hand side of 1 is 0. The limit on the right-hand side of 1 is 1. So that limit does not exist. The next discontinuity we're going to look at is here at 2. So let's look at the limit. So the limit as x approaches 2 on the left-hand side is going to be 1. The limit as x approaches 2 on the right-hand side is also going to be 1. Okay? So at x equals 1, the limit is not going to exist. At x equals 2, the limit does exist, but the limit is not going to equal f of 2. Okay? So we're just pretty much comparing, so the limit as x approaches 2 of f of x does not equal the point at f of 2. That's all that is saying right there. Okay, so continuity at an interior point. So this involves two-sided limits. So the left and the right-hand side limit must equal. So a function y equals f of x is continuous at an interior point c of its domain if the limit as x approaches c of f of x equals c. It equals f of c. So this is pretty much saying that it is not continuous here, because the limit, while it may be 1, it does not equal the defined point. So it is not continuous at this point. Continuity at an endpoint involves one-sided limits. So a function y equals f of x is continuous at a left endpoint a, or is continuous at a right endpoint a, if its domain, the limit as x approaches a from the right of f of x, is f of a. So this is pretty much saying, so we'll go right here. So the limit as x approaches 4 of f of x is going to be the same y value. So the limit as x approaches 4 on the left-hand side is going to be 1, and f of 4 is also 1. That's all that is saying. Also over here, if we're comparing with 1, the limit as x approaches 0 on the left-hand side is 1, and there's a defined point, f of 0 equals 1. So they both match there. So that's telling me that there's continuity at those endpoints. Now let's discuss discontinuities. So if f is not continuous at C, then f is discontinuous at C, and C is the point of discontinuity. Okay, so we already kind of went over there. So C would be 1 and 2, right, in that example. So there's 3 types of discontinuities. There's infinite, which would be an asymptote. So this is done whenever you cross out a reduced fraction and set the denominator to not equal 0, then solve for x. The cross out the reduced fraction, if you crossed anything out, that would be a whole, not a vertical asymptote. And here's a whole. So a removable discontinuity is a function that has a limit and continuous except at the whole. So the terms in denominator that cross out to reduce the fraction. Okay, so these will be the term in a rational expression. So if you had x plus 2, x minus 1 over x plus 2, x plus 3. So the whole would be right there. So x plus 2 can equal 0, solve for x, x can equal negative 2. To find the y value of the whole, which would be an undefined point, you would just put negative 2 into the reduced form. So you would have negative 3 over 1, so your whole would be at negative 2, 3. But it would be a whole, not a defined point. Okay, and these are removable. So you can, just removable just means that if you wanted to make it, you could, there's going to be problems in your exercises where it's going to say, can you removable, how would you make this continuous? You would put the defined point, which would be here, right there. So you would just put a defined point at f of 2 would equal 1. That's what that means. Okay. Jump piecewise, so that's discontinuous, so this is an example of a jump right there. Okay, so let's do some examples. Find the points of discontinuity and the points of discontinuity and identify each type of discontinuity. So when we're identifying, we're seeing if it's infinite, removable, or a jump. So first things first, let's see if we can factor this. So are there factors of 3 that add to get negative 4? Yes. So that's going to be, so we're going to factor. So that's going to be x plus 1 over x minus 1 times x minus 3. Okay, so nothing is crossing out here, so I do not have a whole. Okay, so far this is continuous, but I have something in the denominator. So when I have something in the denominator, that means there's a break in the graph or discontinuity at a graph. So how I find those values algebraically is going to be x minus 1 can't equal 0. X minus 3 can't equal 0. So x can't equal 1 and x can't equal 3. These are going to be an infinite discontinuity. So these are infinite discontinuities. Okay, now if I want, I also need to find the points of continuity. So if I were to draw a number line, so I'm going to write an interval notation. So x can't equal 1 and x can't equal 3. Okay, so there's vertical asymptote here. So when I do my interval notation, my points of continuity are going to be negative infinity to 1, union 1 to 3, union 3 to infinity. So those would be my points of continuity. Okay, or you could say interval of continuity. Next, we have an absolute value function. So if you recall, absolute value function just looks like v, and the domain, if you can remember, is negative infinity to positive infinity. So this is the absolute value function translated to the right 1 unit. So if I could draw this graph, here's 1, looks like that. Okay, so we're looking for points of continuity and points of discontinuity. So there is no denominator and there is no even root radical. So this is going to be, so the points of so this is a continuous function. So it's continuous from negative infinity to positive infinity, and there's no points of discontinuity. Okay, next we're going to do the cube root of 2x minus 1. So you heard me before. So we're looking to see if there's a radical or an even root, a radical of an even root or a denominator. Any one of those, there's going to be discontinuities. However, this is a cubed root. So any odd root, your domain is going to be negative infinity to positive infinity. So again, this is a continuous function. So this is going to be a continuous function. Continuous on all x, which is negative infinity to positive infinity. So, and then there are no points of discontinuity. Now let me do another one. I'm going to add another example. So let's say we have y equals the square root of x plus 4. Okay, this is an even root. So for even roots, algebraically speaking, you're going to do x plus 4 is greater than or equal to 0. Because remember, I can still do the square root of 0 equals 0. So x is greater than or equal to negative 4. This is going to be where my domain is continuous. So it's going to be continuous from negative 4 to infinity. Okay? However, it's going to be discontinuous from negative infinity to about 4. Okay? So that is where it's going to be discontinuous, because then you're going to start getting negative values right here. Okay. Let's look at this example. So this would be example 5. So we're looking at points of continuous function. Let's make this 1 and let's make this negative 2. Okay, so it's continuous. Oops. From negative infinity to about negative 2, union negative 2 to 1, union 1 to infinity. And it's discontinuous at x can equal negative 2. You can put equals negative 2. Sometimes my students get confused on that. So technically, right would probably be x equals negative 2, but you can also say x can equal negative 2 to help your brain think the same. So x can equal negative 2. That's going to be a jump discontinuity. And then x can equal negative 1. That's going to be a removable or a hole. So that's going to be a removable discontinuity. So that's how you determine whether a function is continuous or discontinuous. Next, let's talk about continuous functions for calculus. So what makes a function continuous? So f is continuous at x equals c if the following are true. So we're just looking at a point. So if f of c is defined, that just means it has x and a y value. So you have x and a y. Okay. Also, the limit as x approaches c of f of x needs to be defined. That's just meaning the left and the right limit need to equal the same. Unless it's an endpoint, then the endpoint limits need to be the same as the defined point limits. And then finally, this also needs to happen. So the limit as x approaches c of f of x needs to equal the defined point right here. So that's ultimately going to be how you determine whether a function is continuous or not at a specific value, x value of c. Okay. Also, I want you to note, this is really important, a continuous function does not need to be continuous at every interval. Okay. In calculus, a continuous function does not need to be continuous at every interval. So every function is continuous, but it just might have points of discontinuity. Okay? That's what that means. So polynomial functions are continuous at every real number c, because every real number c, there's going to be a limit with the same y value and the same defined value. So if f of x is continuous at every point, over negative infinity to positive infinity, it is continuous everywhere. Rational functions are continuous at every point of their domains. They just have points of discontinuity at the zeros of their denominator. So let's determine which are continuous. Well, all of these are most likely going to be continuous. They're just going to have points of discontinuity. So if we were to, so the limit, so this is continuous. Continuous. And this is also continuous. But let's take a look. Okay, so I'm just going to get my calculator out so you can see the first function. I'll just draw it on the back of this. So f of x equals x squared minus 4 over x minus 2. So x squared minus 4 over x minus 2. Oops, I'm going to fix my window after it lets me. This should look like a diagonal line. Okay. Okay. Now there is going to be a point of discontinuity at 2. Okay, because there's going to be a hole there. You can't see it, but there is going to be one. Because when you do this, you have x minus 2 times x plus 2. Okay, right there, that's going to be the hole. Okay, to find the y value of the hole, you just put 2 in here. So that's going to be 2 plus 2 equals 4. So when I draw this graph, I have a hole, and plus 2, it's going to be right here. Something like that. Okay, so there's that graph. So it's continuous at every point except at positive 2. Okay, the next one is going to be the same graph except x can't equal 2 and x equals 2 is 3. Okay, so let's see if that's going to make that continuous. So that's just saying, so here's going to be g of x. So we have x squared minus 4 where x can't equal 2 and x equals 2 and y equals 3. So remember, this is equivalent to y, so this is telling you g of x is, or y equals 3 when x equals 2. Okay, so we're almost there. I'm a little bit off over with my hole. So we are a little bit there. So if we were to make this x equals 4, it would be continuous, which is exactly what the next one does. So this is g of x, where x equals 2 and y equals 3. Now we're going to have x equals 2 and 4. So that's when we fill in a dot. Okay, and that is a continuous function. So this is continuous except at x equals 2. That was this one. The other one, the same story. So this is continuous except at x equals 2. Except at x equals 2, and this is continuous everywhere. Okay, and why? Because every other point there's a left and a right limit, and there's a defined point. So all these are defined points. So if I were to get the left hand limit and the right hand limit at this point, it would equal the same value as that defined point right there. The same goes for here. If I was looking for the limit at, let's say, 1. So f of 1 is 2, so if I go to the left and the right side of that limit, I'm also going to get y equals 2. So that's why that is continuous everywhere for each of these. Okay, so now we're going to sketch another graph. Okay, using this information. So we're going to sketch the graph. So we have f of 0 equals f of 2 equals 1. So this is just saying we have defined points at 0, 1, and at 2, 1. We also have a point at 1, negative 1. So let's go ahead and draw those points. So 0, 1, there's a defined point. 2, 1, there's a defined point. And 1, negative 1, there's a defined point. The limit as x approaches 2 from the left-hand side is 0. So as x approaches 2 from the left-hand side, you're going to get 0. I'm pretty sure that's a typo, and it should be negative 2 on the left. Okay, so as x approaches 2 from the left, oh, never mind, 2 from the left is going to 0. Okay, so that means it's going to be so the limit as x approaches 2 from the left, so here's 2. Left of 2, 0. Yes, I'm pretty sure that's supposed to be negative 2. Let's make that a negative 2. So the limit as x approaches negative 2 from the left, so that's going to be 0. The limit as x approaches 0 on the right hand side is going to be 0. Oh, never mind, that is positive 2. So it's approaching 0. So there's going to be another defined point somewhere where it's approaching 0. So 2 from the left, it's approaching 0. So there's something here that's going to approach y equals 0. The limit as x approaches 0 on the right is going to 0. So on the right hand side is going to 0. The limit as x approaches positive infinity is going to go to 2. So this is 1, here's 2. The limit as x approaches negative infinity is going to be going to positive infinity. So somewhere over here. So we have a point 0, 1, 0, 1, 2, 1, yeah, 2, 1, 1, negative 1. Sorry, that should not be there. Okay, so the limit as x approaches 2 from the left-hand side is going to 0. And the limit as x approaches 0 from the right is going to 0. So just block that out. So when we draw this, and then the limit as x approaches infinity is going to 2. So we're going to have something like this. Okay. The limit as x approaches 2 on the left-hand side is going to be 0. So this is the left. Oh, never mind. This should be like this. Two going on the left-hand side is going to positive infinity. So something like that. So this is one way this graph could be done. So I'm going to do this again. Just for a quick review. So 0, 1, 2, 1, 1, negative 1. 2 to the left is going to 0, so I already have a defined point 2, so that means there's going to be some line going here. So 2 to the left is going to 0. And then as x approaches the right hand side of the graph, it's going to be going to 2. Probably looks something like that because it's going down towards the 1. The limit as x approaches 0 on the right hand side is going to be 0. And then the limit as x approaches negative infinity of f of x is going to go to positive infinity. So it's just going to keep going up. Now you can either do this type of thing, or you could go over there. So something that looks like that. Okay, one other example. Oops. So we're going to be finding a value for a so that the function f of the, so that a piecewise function is continuous. So we have f of x equals 2x plus 3 ax plus 1, x is less than 3, x is greater than or equal to 3. So we need to find some value a to make this continuous. So how you do this, you just set this equal to that and then solve for a. So you have 2x plus 3 equals ax plus 1. Well, we have a problem now because we have two variables we need to solve. So, but we do have an x value. We want to point at, this is, all other x values on these graphs are continuous. It's just 3 might be the, I'm wondering if they are or not. Well, to do that, let's just make x equal 3. So 2 times 3 plus 3 equals 3a plus 1. So you have 6 plus 3, which is 9. So this is going to be continuous at 8 over 3. That's where that function will be continuous. Okay. One more thing. The intermediate value theorem. Very important, I can say the word. This will be a justification aspect on the AP exam. Okay. As well as that last problem will most likely be on the AP exam as well. So all the intermediate value theorem says is if you're on an interval from A to B, okay, you're going to have some value C in the middle. So on an interval A to B, you're going to have an area where you're going to have a point in the middle. So function y equals f of x that is continuous on a closed interval A to B takes on every value between f of A and f of B. So f of A and f of B is just the y values of A and the y value of B. Then y equals f of C for some C will be in that domain. So this is C, that's f of C. Okay, that's all that says. Okay, and you don't have to worry about that. Okay, so this concludes the lesson on continuity. I hope you have a great day.